All right, it's 2025, September 30th, approximately 3:38 p.m., continuing along to section 2.4, subgroups generated by subsets of a group. The historical context for this: the notion of generating a group from a subset parallels similar ideas across mathematics. Vector spaces are generated by sets of vectors. Rings by sets of elements. We'll get into that later. Fields, again, we'll get to that later, by extensions of subfields. Now, Galois already considered groups generated by permutations when studying solvability of polynomial equations in the 1830s. Arthur Cayley, in his 1854 memoir, treated groups as an abstract collection of transformations with emphasis on how small sets of generators could build large groups. Camille Jordan, in 1870, classified permutation groups in terms of their generators, making explicit the role of generating sets and describing subgroup structure. Now, by the late 19th century, this perspective was standard. Groups were described by generators and relations, and the way that we always do for looking at dihedral groups, for instance. It was a language crystallized by Walther von Dyck in 1882 when he formalized group presentations. So the language of generation is one of the deepest bridges between algebraic structures and their internal logic. So let's look at this fundamental result of this understanding by looking at a series of propositions. So, okay, let's start with this proposition here. Well, propositions and definitions. We'll start with this proposition. So first off, let the set containing h sub I sub little I of big I be a non-empty, this is a collection, which is why we got the weird, forgot what to call those things. That's why we have the sub I contained within I. So this is a non-empty, let this be a non-empty collection of subgroups of G. Then K is equal to the intersection between all of these subgroups of all of these subgroups of G, H sub I, with I contained within the set I. So that's for indexing purposes, right? This is also a subgroup of G. Now, let's look at the proof of this. So, each A sub I contains 1. So, 1 is an element of K. Now, if A and B are also elements of K, then A and B are elements of H sub I for every I. So, A, B to the negative 1 is an element of H sub I for all I. Therefore, A, B to the negative 1 is contained within K. So by the subgroup criterion, K is a subgroup of G. All right. Now let's move on to subgroup. Let's move on to a definition. So for this definition, let's look at subgroup generated by a subset. So if A is a subset of G, define the group generated by the set A being equal to the intersection with regards to H being a subgroup of G and A being a subset of H. That is to say, the group generated by A is the unique smallest subgroup of G containing A Okay, so there's more that I can say on this. So let's go ahead and erase this and move on to a bit of some intuition here. Intuitively, well, the group generated by A is obtained essentially by closing the set A under the group operation and inverses. It's minimal in the sense that if H is a subgroup of G and A is a subset of H, then the group generated by A is a subset of H. Okay? So that's pretty cool, right? So let's get into another proposition. So which, if I didn't note, which I really should have, yeah, this section is titled Subgroups Generated by Subsets of Groups. So that's going to be all about that. So let's talk about this proposition here. Let A be a subgroup of G. Then what do we have? Well, that which is generated by, well, the group generated by A, that's equal to the set containing A sub 1 to the epsilon sub 1, A sub 2 to the epsilon sub 2, times on and on and on until we reach A sub n to the epsilon sub n, such that n is greater than or equal to 0. A sub 1 is contained within the set A, A sub I is contained within the set A, and epsilon sub I is contained within the set containing plus or minus 1, and only those two things. So, in other words, that is to say, i.e., the group generated by A consists of all finite products of elements of the set A and their inverses. So let's look at a proof of that, right? I mean, that's pretty extraordinary if you think about it, but I mean, that's what we found. Okay, so for the proof of this, the set on the right-hand side, so that set of like, you know, a sub 1 to the epsilon sub 1, a sub 2 to the epsilon sub 2, that's non-empty. It's not empty, contains 1, let me think about that. A sub 0 such that is an element, well, it contains the identity, in which case we're representing that with 1, which is true. So yeah, so the set on the right is non-empty, it contains the identity, it's closed under products. We could look into this every bit at a time, but we'll look into that for the exercises. That's where we get more of the rigor. But for now, suffice to say, just say it's, you know, it's not empty, contains the identity, it's closed under products, and closed under inverses. So it's a subgroup containing A, the set A. By minimality of the group generated by the set A, they coincide. Okay. So now this is kind of a rough sketch of a proof, but you know, go through it, see what you think. And we'll get into the exercises. So let's look at exercises for now. I mean, not exercises, examples for now. So first up, if A is equal to the set containing X and only X, then the group generated by A is the group generated by X. And this is the cyclic subgroup generated by X, the cyclic subgroup. Now for another example, in the dihedral group of 8 elements, D sub 8, which is equal to the, well, I mean, we're going to leave out the relations, I guess, for now. Well, we'll get back to it. So, which is generated by R comma S. So we also have that, we also have the dihedral group D sub 8 is equal to the group generated by S and RS. So different generating sets can define the same subgroup. Okay? So different generating sets can define the same subgroup, of course, but let's get into another example here. I'm just going to erase this because we need more space. Now, in S sub n, the symmetric group, the group is generated by just 2 elements. right? We've looked at this, and the first one is the transposition. So that's open parentheses, 1, 2, then 2, close parentheses, and the end cycle, open parentheses, 1, then 2, then dot, 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 all the way up 10, close parentheses. For example, in the general linear group over the reals with degree 2, the matrices A is equal to, from left to right, top to bottom, 0, 1, 1, 0, and B, 1, 0, 1, 0, 0, negative 1, both have order 2, but subgroup A, comma B, the subgroup generated by A, comma B is infinite. Now, this illustrates the complexity that can arise when generators do not commute. I should make note of that. I'll just say shows. Shows the complexity that can arise when generators do not commute. All right. So, and that's pretty much it for section 2.4. The subgroups generated by subsets of a group. Now let's move on to 2.5. 2.5 is an interesting one. I mean, they're all fairly interesting, but this one is just like we get these interesting diagrams. So for section 2.5, which is on the lattice of subgroups of a group, now, for historical context, the visualization of subgroup structure as a lattice dates back to the late 19th and early 20th centuries, right? When all this stuff is sort of coming about, when group theory and lattice theory began to interact, which is, it's pretty interesting. Lattice theory, its own thing, is pretty funny. I mean, it's interesting to think about, but Richard Dedekind, who lived between 1831 to 1916. I mention the dates just because it's convenient to mention at the time in which it is convenient to mention them. But he studied subgroup systems with an eye toward modular laws, laying groundwork for what would later become lattice theory. Now, Ernst Steinitz, a name which I haven't mentioned before in this context, who lived between 1871 and 1928, and contemporaries in the early 20th century emphasized subgroup lattices in connection with field extensions, anticipating the structural role they play in Galois theory, for instance. By the mid-20th century, subgroup lattices had become a central visual and theoretical tool. And you can sort of see this whenever you look at crystallography, for instance. I mean, it's kind of a bit arbitrary, but it's kind of there. So, continuing on where I left off with important classification work. So, for example, that done by Marshall Hall Jr., who lived from 1910 to 1990, relying on lattice diagrams to organize subgroup inclusions. So, here's the thing. Subgroup lattices remain a primary way of visualizing the internal symmetry of a group, and we'll see that. But let's start with a nice definition first. So, to start, let's define subgroup lattices. So the lattice of subgroups of a group, big G, capital G, is the partially ordered set of all subgroups of capital G, the group G, ordered by inclusion. And let's see here, it's typically drawn is the partially ordered set. Yeah, it's essential that I put this comma here because it is a drawn thing. So it's typically drawn as a diagram with edges representing maximal containments. Not exactly a nursing home, but you could probably discuss or define a nursing home in the same way. But maximal containments. No. But yes, that's how we define a lattice. Let's look at some examples of this. And I don't think this is too often a thing which was discussed, just because, like, I don't know, there could be applications of it, but I just know that in my experience, it wasn't really discussed all that much. I think I had like maybe one homework problem when I had a homework problem on this, and it's like, it's just one, which, you know, is nice, but I would have liked to have heard more about it in a lecture, but now you do. So let's look at examples of these for cyclic groups. So for cyclic groups of small order, a subgroup lattice is determined by divisors of n. Divisors of n. So for instance, this is how we'd show the integers mod 2. It's equal to the group generated by 1, and we do this line here and show that, okay, the group generated by 2, what is that equal to? That's equal to the set containing 0. So that's what we do for the integers mod 2. Now I'll show you various cyclic groups in lattice, lingua franca. No, but it's not even said properly. But for instance, the integers mod 4 is equal to, equal to the group generated by 1. So we could note here that the group generated by 1 is equal to the group generated by 3 in this case. And then so we have group generated by, we have line, then group generated by 2, then line, then group generated by 4, which is equal to the set containing 0 and only 0, right? Now let's take a look at another one, which is integers mod 8. So this is also generated by the group containing 1, and special thing to note here, to pay attention to, it's like, well, the group generated by 1 is equal to the group generated by 3, which is equal to the group generated by 5, which is equal to the group generated by 7 in this case, okay? That follows. And this here is group generated by 2, line, group generated by 4, line, group generated by 8, which is equal to the set containing 0 and only 0. So you're beginning to see a pattern of how the lattice, I guess, notation, lattice diagram works. So now here's an interesting one. So in general, if P is a prime, the lattice of the integers prime, mod prime is, you can probably guess it, because there's all these sort of disjoint things here, which is like the integers mod P being prime to some power n is equal to, it's still generated by the set containing 1 and only still generated by 1, which is equal to the set generated by P, which is equal to the set generated by P squared, which is equal to the set, well, no, not equal to, I'm just saying line, then line, then line, then, and this goes on and on and on until we reach, you know, P to the n minus 1, the group generated by P to the n minus 1, and then we get the group generated by P to the n. And this finally is equal to the set containing 0 and only 0, right? So that's pretty neat. Now, let's just keep going. Let's take a look at another such group. How about, you know, the integers mod 6 is generated by 2, generated by 3. This is an interesting one, and then generated by 6, finally. It's equal to the set containing 0, right? So, let's go back to how we define this a lot more specifically, right? So, the lattice of subgroups of G, of a group G, is the partially ordered set of all subgroups of G ordered by inclusion, typically drawn as diagram with edges representing maximal containment. So, that makes sense. Maximal containment's there. Now, yeah, and that's why it should be interesting that for the cases in which you find things that are equal to one another, the groups generated by specific elements are equal to one another. We don't list those other ones out, though we could, right? It's implicit, it's carried within the notation. So, let's look at another one real quick. The integers mod 12. So, it's like the group generated by 2, the group generated by 3. There we go. So the group generated by 6. How about the group generated by 4? How about the group generated by 12? And that would be equal to the set containing 0. Okay? Now, here's an interesting example, another interesting example. This section is mainly just examples, because I mean there's just so much to look at in terms of lattices. I mean the purpose of it is it's a visual, so it's not too surprising. Example, the Klein 4 group, which pops up a lot. Okay, so the Klein 4 group, which is denoted as V sub 4, I think that's because of German reasons, which is equal to the set, which is just like amazing that set theory, I mean that group theory survives. It's like, you know, all the badness. But that's equal to the set containing 1, A, comma, B, comma, C. That has a multiplication table. So this Klein 4 group has a multiplication table. Let's just put that right out there. And this multiplication table, what does it look like? Well, like so. So we have 1, A, B, C, 1, A, B, C, right? Top to bottom, left to right. 1, A, B, C, that's pretty self-evident, but then we have A, 1, C, B, then we have B, C, 1, A, then we have C, B, A, 1. Okay. What does its lattice look like? Well, the lattice looks like this. So you have our notation V sub 4 is generated by you have line and then group generated by A, line, then group generated by B, line, then group generated by C. And then finally, all of these connect via one line. Now, each has their own line, which connects to the identity, right? So that's pretty cool. Now let's talk about the subgroup lattices of three fundamental groups in particular. Those being S sub 3, so the symmetric group with 3 elements, the dihedral group with 8 elements, and the quaternion group. So their sublattices are, we'll start with the symmetric group here, symmetric group of 3 elements. So let's go left to right. So that generated by the cycle, open parentheses, 1, then 2, close parentheses. Then that generated by open parentheses 1, then 3, close parentheses. That generated by 2, then 3, close parentheses. And that generated by open parentheses 1, then 2, then 3, close parentheses. Right? And all of these go, so all of these have their own line to the identity. So that's pretty cool. Now, let's take a look at the dihedral group with 8 elements. This one's a bit prettier, so I like this one. I think this one might be one of my favorites. So the dihedral group, let's go right, and because it kind of reminds me of merge sort in a way, but so we have like recursive trees, binary trees. So the group generated by S and R squared, gonna need more space. Telling you right now. Okay, so go all the way over there. The group generated by S and R squared, group generated by R, group generated by, I should be saying subgroup, right? Subgroup generated by RS, R squared, then subgroup generated by S, subgroup generated by R squared, S, subgroup generated by R squared, and each one has a line to each one of the ones which previously existed on the previous level, right? So, and the subgroup generated by RS, subgroup generated by R cubed S, right? And all of these have their own line to the identity element. So that's pretty cool. I think that one's definitely one of my favorites. The dihedral groups in general are my favorite because they're just they're just pretty to look at. Now, let's look at the quaternion group. So for the quaternion group, we have, of course, group generated by I, the subgroup generated by I, the subgroup generated by J, the subgroup generated by K. Let's see, am I saying this right? Yeah. Lattice of subgroups, typically drawn as a diagram with edges. So sometimes you'll show like, I gotta be careful because I remember like in the exercises, one of the think, so you can draw these lines. I think there's like specific cases where you can draw double lines to represent something else, but we'll discuss that later. But anyhow, so we have each of these subgroups, that which is generated by I, that which is generated by J, that which is generated by K, and each of these have their own line to the identity. Well, no, sorry, to the subgroup generated by -1, which then has its own line to the identity. So let's look at two final ones, and then we'll call it a day for chapter 2. Chapter 2, at least the lecturing part, the overview part. So let's look at the dihedral group with 16 elements. Now, the lattice of subgroups of D sub 16 cannot be drawn planar without crossings. Cannot be drawn planar without crossings. And you know, that's got to be one heck of a proof, right? I mean, but you can just look at it and you can sort of, but you know, it's not proof. I mean, it used to be. So let's say you have D16, D sub 16 up here. I don't know if I'm going to have enough room, but one line to R, one line to a group generated by S comma R squared, another line to that group generated by SR comma R squared. Right, and these go to their own things. In this case, group generated by SR squared comma R to the power 4, and then S comma R to the 4, right? And then finally we have that which is generated by R squared going there, and then SR cubed R to the 4th, that goes there. Then this thing goes SR to the power 5, R to the power 4, right? And here's what I mean about crisscrossing here with a second to last level. So I actually can kind of fit, well, you know, don't count your eggs before they've hatched in a sense. Don't count your chickens either. But the group generated by SR to the 6th, SR to the to the power 2, coming from here, SR to the power of 4 coming from here, and then, oh goodness, S coming from here, group generated by S coming from there, group generated by R to the power 4 is coming from there, and here's where we get into some trouble. Well, if by trouble you mean intersecting lines. So this goes here, all right? So this also connects here. The group generated by 4 also connects here. It also connects here. So it's that the group generated by R to the power 4, which causes the problems. But and this goes to group generated by S R to the power 3, S R to the power 7. This has S R to the power 5 and S R. And all of these, of course, you could probably guess what they connect to. And if you guessed the identity, you'd be correct. So for the final example, I'll say this. You could draw this quite easily as something else. So sometimes, I'll make this little note, sometimes only a relevant portion of the lattice is needed. For instance, For instance, focusing on the relation between that group generated by S comma R squared and the subgroup generated by R squared yields this, which is D sub 16. Then we have to draw a line to subgroup generated by S comma R squared, and then we draw a line to the group generated by S R squared comma 4 R to the power 4 the group generated by subgroup generated by that, and then the subgroup generated by R squared, and each of these has a line to the group generated by R to the power 4, and this has a line to the identity, and that's pretty much it. So we represented by narrowing our focus. We have a satisfactory lattice drawn by something more appropriate to the focus, right? So that concludes basically all of what I have to say in the overview for chapter 2 on subgroups, and that is it for now.